Let's talk about endings, not the gradual fade-out kind, where things decline slowly over millennia until they just sort of peter out. No, we're talking about the kind of ending that hits like a cosmic sledgehammer, the kind that divides Earth's history into before and after with a precision that geologists can measure in centimetres of rock. 66 million years ago, on what was probably a perfectly ordinary Tuesday in the late Cretaceous, something happened that would fundamentally reset life on Earth. An asteroid roughly 6 miles across, travelling at speeds that would make a bullet look stationary, slammed into what is now the Yucatan Peninsula in Mexico. The impact site is called Chicxulub, and if you could see it from above, stripped of ocean and sediment, you'd be looking at a crater 93 miles wide and 12 miles deep. That's not a crater. That's a wound in the planet itself. But here's what really gets me about this event. It wasn't the asteroid itself that killed the dinosaurs, not directly. Sure, anything within a few hundred miles was instantly vaporized, but that's not what caused a mass extinction. What happened next? That's the real killer. The impact released energy equivalent to about 10 billion Hiroshima bombs. Let that sink in for a moment. 10 billion. The explosion ejected roughly 25 trillion metric tons of debris into the atmosphere. Rock that had been solid ground seconds before was now superheated vapor, molten droplets, and pulverized dust. All of it thrown into the stratosphere at velocities that briefly escaped Earth's gravity before raining back down across the entire planet. Within hours, the sky everywhere on Earth was on fire. Those molten droplets falling back through the atmosphere created a global infrared pulse that essentially turned the planet's surface into a broiler. Forests around the world spontaneously combusted. Animals that had been going about their business thousands of miles from the impact site suddenly found themselves in a world where the air itself was hot enough to kill. The dinosaurs that survived the initial firestorm probably thought the worst was over. They were wrong. Because here's the thing about throwing 25 trillion metric tons of debris into the atmosphere. It doesn't just fall back down and disappear. The finest particles, the ones microscopic enough to stay suspended in the upper atmosphere, they blocked out the sun. Not partially. Not like a cloudy day. We're talking about darkness so complete that photosynthesis became impossible across most of the planet. Scientists call this impact winter, which sounds almost cozy until you understand what it actually means. Imagine night lasting not for hours but for months, maybe years. The evidence suggests that global temperatures dropped by as much as 50 degrees Fahrenheit in some regions. In the span of weeks, Earth went from a greenhouse world, warm and humid and teeming with life, to something closer to a frozen wasteland. The plants died first. Without sunlight, photosynthesis stops. Without photosynthesis, plants starve. The fossil record shows this with brutal clarity. Pollen samples from rock layers just above the impact show a catastrophic collapse in plant diversity. Species that had dominated landscapes for millions of years simply vanish from the record. In their place, we find massive spikes in fern spores. Ferns, those hardy survivors that can grow from underground rhizomes even after surface vegetation is destroyed. When the plants died, the herbivores followed. The great horned dinosaurs, the duck-billed hadrosaurs that had roamed in herds thousands strong, the armored ankylosaurs. They needed hundreds of pounds of vegetation daily just to survive. Within weeks of the impact, they would have been starving, within months dead. And when the herbivores died, the predators followed. The tyrannosaurs, the raptors, all those magnificent killing machines that had ruled terrestrial ecosystems for over 160 million years. They starved too. Not quickly, because large predators can survive for weeks without food, which means they probably lingered, hunting through forests of dead trees and fields of rotting corpses, finding less and less to eat until one by one they fell. 75% of all species on Earth went extinct. Not gradually, not over thousands of generations, but in what geologists call an instant, which in geological terms means maybe a few thousand years, but probably much less. The boundary between the Cretaceous and Paleogene periods, between the age of dinosaurs and the age of mammals, you can literally put your finger on it. It's a thin layer of clay found in rock formations around the world, usually just a few centimeters thick, enriched with iridium, an element rare on Earth's surface but common in asteroids. Above that layer, dinosaur fossils. Below it, nothing but mammals and birds and the survivors. That line represents the day the world ended. But here's where the story gets complicated, because endings are never as simple as they first appear. Some things survived, not by being strong or fierce or specialized, but by being small, adaptable, and in many cases just plain lucky. Small mammals, most of them no bigger than rats, made it through. They could shelter underground. They could survive on insects and seeds and detritus. They didn't need vast territories or enormous food supplies. When the world was ending, being small and unspecialized turned out to be the greatest survival trait possible. Birds survived too, though just barely. The fossil record suggests that most bird lineages went extinct, probably because the ecological niches they depended on collapsed. But some made it through, mostly smaller ground-dwelling species that could eat seeds and insects. These survivors would eventually evolve into the 10,000 bird species we have today, but in the immediate aftermath, they were just handfuls of traumatized populations clinging to existence in a devastated world. Crocodiles and turtles survived, probably because they could go for long periods without food and tolerate extreme environmental conditions. Sharks and many fish species made it through because ocean ecosystems, while severely damaged, weren't quite as catastrophically disrupted as terrestrial ones. The ocean has a way of buffering environmental extremes. But here's what really haunts scientists about this event. The fossil record from the immediate aftermath is incredibly sparse. We're talking about one of the most important transitions in Earth's history, and we have huge gaps in our understanding of what actually happened in the years and decades following the impact. Part of this is just bad luck. Fossilization requires very specific conditions. Dead organisms need to be buried quickly in sediment, protected from scavengers and decay, then subjected to just the right chemical conditions over millions of years. During the chaos after the impact, these conditions were rare. Ecosystems were disrupted, erosion rates changed. The normal processes that create fossils were themselves in crisis. But there's another factor too. After the impact, there simply weren't that many organisms around to fossilize. When 75% of species go extinct, population numbers crash even more dramatically. The survivors weren't thriving. They were barely hanging on, scattered in whatever refugees still supported life. Small populations leave few fossils. So we have this maddening gap in the record. We can see the world before the impact, thriving and diverse. We can see the impact layer itself, that thin band of iridium-rich clay marking the day everything changed. And we can see what emerged millions of years later after the recovery. But the transition itself, those crucial years and decades and centuries when surviving species were adapting to a transformed world, when ecological relationships were being completely rearranged, when the stage was being set for everything that would follow. That period is frustratingly obscure. What we do know is that the world that emerged from the impact winter was fundamentally different from what came before. The climate was unstable, swinging between extremes as the planet's systems tried to find new equilibrium. The forests that eventually grew back were different species, adapted to different conditions. The animals that survived radiated into new forms, filling ecological niches left empty by the extinctions. But there's also scientific debate about whether the asteroid was the only cause of the extinctions. Some researchers point to massive volcanic eruptions in what is now India, the Deccan Traps, which were already pumping huge quantities of greenhouse gases into the atmosphere for hundreds of thousands of years before the impact. These eruptions might have already stressed ecosystems, making species more vulnerable when the asteroid hit. Others suggest that the impact triggered secondary effects that were just as deadly as the initial disaster. Massive tsunamis that scoured coastlines, acid rain from vaporized sulfur-rich rocks that poisoned freshwater systems, wildfires that may have consumed 70% of the world's forests. Each of these would have caused its own cascade of extinctions, and they all happened essentially simultaneously. The truth is probably that it was all of these things together. The asteroid didn't hit a healthy planet, it hit one already stressed by volcanic activity and climate change. The impact didn't just kill directly, it triggered a cascade of secondary disasters that compounded each other. And the result was the most thorough extinction event since the end of the Permian, 250 million years earlier. But here's what makes this ending also a beginning. Those small mammals that survived, those ground-dwelling birds, those adaptable generalists who made it through the worst catastrophe in 66 million years, they inherited an empty world. A world without tyrannosaurs, a world without massive herbivores competing for vegetation, a world of opportunities. Within a few million years, which is nothing in evolutionary terms, those rat-sized mammals had diversified into forms that would have seemed impossible in the dinosaur-dominated world. Predators, herbivores, species that climbed trees, species that swam, species that eventually grew to enormous sizes themselves. One lineage of these survivors would eventually evolve into primates, and millions of years later into apes, and eventually into us. Every human alive today is a direct descendant of whatever tiny, frightened mammals were hiding in burrows or hollow logs on that terrible day 66 million years ago. We exist because dinosaurs died. Our whole evolutionary story, everything that makes us human, only happened because an asteroid happened to hit Earth at exactly the right angle, at exactly the right place, at exactly the right time to wipe out the dominant life forms and give our ancestors room to evolve. But as we stare at that thin layer of clay in the rock record, as we try to piece together what happened in the chaotic years that followed, we're confronted with a profound mystery. One of the most important transitions in the history of life on Earth, and we can barely see it. The fossil record goes quiet right when things get most interesting. The world ends, the world begins again, and most of the details are lost to time. This is just the first gap, the first place where the story of life on Earth becomes frustratingly unclear. And it won't be the last. So the asteroid hits, the dinosaurs die, the dust settles, and then what? This is where the story should get clearer, right? The slate's been wiped clean. Life starts over. We should be able to watch evolution happen in real time, see new species emerging from the ashes like a perfectly documented origin story. Except we can't. Because the Paleocene, those first 10 million years after the extinction event, is when the fossil record decides to become frustratingly, maddeningly incomplete. Here's what we know happened. In the immediate aftermath of the impact, maybe 75% of all species on Earth went extinct. The big ones died fast. The small ones, the ones that could hide, that could eat almost anything, that could survive on scraps, those hung on. Mammals were among the survivors, but they weren't the mammals you're picturing. These were tiny creatures. Most were no bigger than a rat. Some were as small as shrews. They'd spent 160 million years living in the shadows of dinosaurs, evolving to be small, to be quiet, to be nocturnal, to be invisible. Then suddenly the dinosaurs were gone and the world was empty. Think about what this means. You're a small mammal, maybe 2 pounds soaking wet. Your entire evolutionary history has been about staying small, hiding from predators that could swallow you whole. Then one day those predators are just gone. All of them. Every single dinosaur that wasn't a bird, wiped out. The forests are burned. The landscape is devastated. But you're alive. And for the first time in your species' entire existence, nothing is hunting you. What would you do? You'd expand. You'd grow. You'd evolve. And that's exactly what happened. Within the first million years of the Paleocene, mammals began getting bigger. Not dramatically, not yet, but measurably. Species that had been mouse-sized started producing descendants that were rabbit-sized, then dog-sized. The evolutionary pressure that had kept them small for millions of years, that constant threat of being eaten, it was gone. But here's where the fossil record starts playing tricks on us. We should be able to track this transformation step by step. Watch these tiny survivors gradually becoming larger, diversifying, filling the empty ecological niches left by the dinosaurs. And we can, sort of, but only in fragments, only in pieces so incomplete that scientists spend entire careers arguing about how they fit together. Take the issue of timing. How fast did this growth actually happen? Some fossil sites suggest rapid evolution, mammals doubling in size within a few 100,000 years. Other sites show much slower change, gradual increases over millions of years. Which is correct? We don't know, because we don't have continuous fossil records from enough locations to be sure. We have snapshots, moments frozen in stone, separated by hundreds of thousands of years of missing time. It's like trying to watch a movie where 90% of the frames have been cut out. You see the opening scene, dinosaurs everywhere, cut to black. Next frame, they're gone and small mammals are scurrying around the ruins. Cut to black. Next frame, those mammals are suddenly bigger, diversifying into different forms. Cut to black. Next frame, you've got creatures that look nothing like anything that came before. The gaps aren't just annoying, they're hiding crucial evolutionary transitions, the moments when one thing became another thing, the exact sequence of changes that turned a tiny shrew-like mammal into something that could eventually become a horse, a whale, a bat, a primate. We know these transformations happened during the Paleocene. We just can't see them happening. Meanwhile, the planet itself was going through dramatic changes. The forests were coming back. Not the same forests that existed before the impact. Those were gone, their seeds and saplings incinerated in the global firestorms. But new forests, growing from whatever survivors had made it through. Ferns were among the first plants to reappear. They reproduced through spores that could survive extreme conditions. Within a few thousand years, vast fern prairies covered what had been barren landscapes. Then came the flowering plants, the angiosperms. They'd been relatively minor players before the extinction. After it, they exploded in diversity, becoming the dominant plant form across most of the planet. This created entirely new ecosystems that had never existed before. and mammals were evolving to exploit them in ways that would have been impossible under dinosaur rule. Some mammals became specialized browsers, eating leaves and shoots. Others became frugivores, feeding on the abundant fruits produced by flowering plants. Still others became predators, hunting the other mammals that were multiplying in the dinosaur-free world. But we're missing most of the details. We know these adaptations happened because we find fossils of mammals that clearly had them. Teeth designed for grinding plants, limbs adapted for climbing trees, bodies built for running down prey. But the intermediate forms, the species that bridge the gap between the generalized survivors and these specialists, they're largely absent from the record. Why? Part of it's simple bad luck. Fossilization requires very specific conditions. An animal dies, gets buried quickly before it decays or is scavenged, stays buried in sediment that eventually turns to stone, then somehow gets exposed millions of years later, where paleontologists can find it. Each step in this process is unlikely. Most organisms that ever lived never fossilized. They died, decayed, and disappeared without leaving any trace. But the Paleocene seems to have been particularly bad for fossil preservation. The environmental chaos following the extinction created conditions that actually made fossilization less likely in many areas. Sea levels were fluctuating wildly. Climate zones were shifting. The stable depositional environments where fossils form best, river deltas, lake beds, shallow seas, they were constantly being disrupted. So we're left with tantalizingly incomplete evidence. We find a fossil here, another one 1,000 miles away, a third one separated from the first 2 by 2 million years, and we try to connect them into a coherent story. But the connections require speculation, educated guesses based on anatomy, on evolutionary theory, on comparison with living animals. We can make reasonable inferences, but we can't be certain. And then there are the creatures that show up in the Paleocene fossil record, dominate for a while, and then just vanish. Entirely. No descendants, no clear explanation for why they went extinct. They're evolutionary dead ends, experiments that didn't work out, wiped from the story as thoroughly as the dinosaurs themselves. Consider the multituberculates. These were mammal-like creatures that had actually survived from the dinosaur era. They'd been around for over 100 million years, making them one of the most successful mammal groups in history. In the early Paleocene, they thrived. They grew larger, diversified, filled ecological niches from underground burrowers to tree-dwelling plant-eaters. Fossil evidence suggests they were everywhere, possibly the most common mammals on Earth. Then they disappeared. Sometime during the Paleocene or early Eocene, the multituberculates went extinct, all of them. Every species. We don't know why. We don't know exactly when. We don't even have good fossils showing their decline. They're just there in older rock layers and absent from younger ones. 120 million years of evolutionary success wiped out during Earth's recovery period, and we missed it happening. They're not alone. The Paleocene is full of these ghost lineages, mammals that evolved, thrived briefly, then vanished without descendants. Creatures that would have seemed bizarre to modernize, early ungulates that don't clearly connect to any living hoofed mammals, carnivorous mammals that weren't ancestors of modern carnivores, primates that branched off our family tree and then disappeared completely. Each of these extinct lineages represents millions of years of evolution that led nowhere, at least nowhere we can see. And each one is documented primarily through fragments. A jaw here, a few teeth there. Maybe, if we're really lucky, a partial skeleton. Never enough to fully understand what these animals were, how they lived, or why they failed. Meanwhile, the climate was doing something extraordinary. For most of the Paleocene, temperatures were relatively cool by post-extinction standards. Not Ice Age cold, but cooler than the late Cretaceous had been. The planet was recovering, but slowly. Ecosystems were rebuilding piece by piece. Then, right at the end of the Paleocene, about 56 million years ago, something dramatic happened. Global temperatures suddenly spiked. Not over millions of years, over thousands of years, maybe even faster. This event, called the Paleocene-Eocene thermal maximum, or PTM, saw average global temperatures rise by 5 to 8 degrees Celsius in a geological instant. The effects were catastrophic. Ocean chemistry changed, becoming more acidic. Deep-sea creatures experienced mass extinctions. On land, entire forests migrated poleward, following their preferred temperature ranges. Tropical conditions extended far into what are now temperate zones. And mammals, those survivors who'd been steadily diversifying for 10 million years, suddenly faced a new crisis. We should be able to see how they responded in detail. Watch them adapt, migrate, evolve new heat tolerance mechanisms, track the species that made it through versus those that didn't, and we can, sort of. But the fossil record from the PTM is, once again, frustratingly patchy. We have some excellent sites that preserved snapshots of the event. The Bighorn Basin in Wyoming, some locations in Europe, a few spots in Asia, but vast regions of the planet have no fossil record from this period at all. So we know the PETM happened. We know it caused major evolutionary changes. We know mammals responded by evolving smaller body sizes, an adaptation to heat stress. We can even identify some new species that emerged during this period. But we can't see the full picture. Can't track how changes in one region connected to changes in another. Can't identify which evolutionary innovations were direct responses to the warming versus which were just happening coincidentally. It's like trying to understand a pandemic by only having medical records from 3 cities. You can see that something major occurred. You can identify some of the patterns, but you're missing most of the data, most of the story, most of the connections that would let you really understand what happened and why. And this is the fundamental frustration of the Paleocene. We know this was one of the most important periods in mammalian evolution. The time when our distant ancestors went from tiny survivors hiding in the rubble to diverse creatures beginning to dominate terrestrial ecosystems. The 10 million years that set the stage for everything that came after, including eventually us. But we're watching it happen through a keyhole, catching glimpses, missing the crucial moments. Scientists have been working on this problem for over a century. Every year, new fossil sites are discovered, new species are described, new connections are proposed. The picture gets slightly clearer, slightly more detailed, but the gaps remain, and some of them might never be filled. Some of the species that evolved during the Paleocene might have lived in environments that simply don't preserve fossils well. Upland forests, mountain regions, areas that have since been subducted beneath tectonic plates or eroded away entirely. Those species, those evolutionary experiments, those crucial transitions, they're gone. Not just gone from Earth, but gone from any possible record of Earth's history. They existed, they mattered, they contributed to the evolutionary path that led to modern mammals, but we'll never know their details, never see them as more than gaps in the story, blank spaces between the fragments we've managed to recover. This is what makes the Paleocene both fascinating and frustrating. It's Earth's recovery period, the time when life bounced back from the worst disaster in millions of years. It's proof that evolution can rapidly fill empty ecological niches, that mammals could transform from marginalized survivors to planetary dominance in just 10 million years. It's the foundation for everything that came after. But it's also a reminder that deep time doesn't preserve itself neatly for our convenience, that the past is mostly lost, that even during periods we desperately want to understand, periods crucial to our own origins, the universe doesn't care about leaving us a clear record. What we're left with is an outline, a sketch where there should be a detailed painting. We know mammals diversified. We know forests returned. We know the climate warmed catastrophically at the period's end. We know some lineages succeeded while others failed. But the mechanisms, the precise sequences, the individual stories of adaptation and extinction, most of those are hidden, locked in rocks that no longer exist or buried in sediments we haven't found yet. The Paleocene is Earth's recovery period, but it's also paleontology's most beautiful mystery, a time when everything changed and we missed watching it happen. Because here's the thing about the world after the dinosaurs. It didn't just recover, it went completely insane. We're talking about a version of Earth so different from what we know that it might as well be an alien planet. And the strangest part, we barely understand how it happened or why it ended. The Eocene epoch, 56 to 34 million years ago. The name means dawn of the recent, which is almost funny because there was nothing remotely recent about the conditions on Earth during this time. This was the last period when our planet was a true hothouse world. No ice anywhere, not at the poles, not on mountains, nowhere. The entire planet was a greenhouse. Picture this. You're standing in what will one day be Alaska, but instead of tundra and permafrost, you're surrounded by palm trees. Actual palm trees swaying in the warm Arctic breeze. The temperature, a comfortable 70 degrees Fahrenheit, in the Arctic, all year round, because during the Eocene there were no seasons as we know them. The global climate was so warm that temperature differences between the equator and the poles were minimal, maybe 20 degrees instead of the 100-degree difference we see today. Crocodiles swam in rivers where London now stands. Alligators basked on riverbanks in Wyoming. Lemur-like primates climbed through rainforests that covered what is now the American Midwest. The Arctic Ocean was warm enough to swim in, sometimes reaching temperatures of 70 to 75 degrees Fahrenheit at the surface. For comparison, that's warmer than modern California beaches. But here's where it gets really strange. We don't fully understand why the Eocene was so warm. Yes, atmospheric carbon dioxide levels were higher, maybe 1,000 to 2,000 parts per million compared to today's 420 parts per million. But the climate models don't fully add up. Even with elevated CO2, the temperatures at the poles were way higher than our models predict they should have been. There's something missing from our understanding. Some feedback mechanism in Earth's climate system that we haven't figured out yet. A gap in our knowledge about how the planet regulates heat when it gets this warm. And this wasn't a short period. The Eocene lasted 22 million years. For context, that's longer than the entire time between the asteroid impact that killed the dinosaurs and the beginning of the Eocene. 22 million years of unbroken tropical conditions worldwide. 22 million years for life to adapt to this hothouse world and evolve into forms we can barely recognize. The mammals that emerged during the Eocene were like nothing that exists today. And I mean nothing. Sure, there were early versions of groups we recognize. Primitive horses the size of dogs, early whales that still had legs and walked on land, ancient primates experimenting with life in the trees. But there were also entirely new groups of mammals that have no modern descendants, lineages that thrived for millions of years and then vanished completely, leaving behind only fragments of fossils and massive questions about what they were and how they lived. Take the creodonts. These were the apex predators of the early Eocene, filling the ecological roles that big cats and wolves fill today. But they weren't related to modern carnivores at all. They were a completely separate evolutionary experiment in being a meat-eater. Some were massive, bigger than modern lions. Others were small and weasel-like. They dominated for millions of years and then disappeared around 35 million years ago, replaced by true carnivores, the ancestors of modern cats and dogs and bears. We don't know why the creodonts died out. We don't know why true carnivores were more successful. We just know that one group replaced the other, and millions of years of evolutionary history went extinct without leaving clear explanations in the fossil record. Or consider the Brontotheres. Imagine a rhinoceros, but stranger. Much stranger. These massive herbivores looked like someone took a rhino and gave it elaborate Y-shaped horns, then scaled it up until some species were 8 feet tall at the shoulder and weighed 4 tons. They were everywhere during the Middle Eocene, dominating North American and Asian ecosystems. Then, around 34 million years ago, they all disappeared within what seems like geological seconds. The entire family, dozens of species, gone. The fossil record shows them thriving 1 million years, then absent the next. What happened? Climate change? Disease? Competition with other herbivores? Nobody knows. The gap in our understanding is total. And here's the really frustrating part. The Eocene should have left us an incredible fossil record. Warm, wet conditions mean lush vegetation, abundant life, lots of animals dying and getting buried in sediments. But instead, the Eocene fossil record is full of holes. Massive gaps where we should have thousands of specimens, but instead have handfuls. Critical transitional periods where we'd love to see how species evolved but find almost nothing. Why? Partly it's geology working against us. The Eocene was a time of intense geological activity. Continents were moving faster than at almost any other period in Earth's history. India was slamming into Asia, creating the Himalayas, and in the process destroying or burying countless fossil beds. The Atlantic Ocean was widening, pulling North America and Europe apart, subducting seafloor and taking fossil-bearing sediments down into the mantle, where they'd be melted and destroyed. The Rocky Mountains were being uplifted, tilting and fracturing rock layers, mixing up the geological record until figuring out what happened when became nearly impossible. But it's also the environment itself. Tropical rainforests, which covered huge portions of Eocene Earth, are terrible for fossil preservation. The heat and moisture cause bodies to decompose rapidly. The acidic soils dissolve bones. The constant growth and decay of vegetation churns up the ground, destroying burial sites. Modern tropical rainforests are among the most biodiverse places on Earth, but they produce almost no fossils. The Eocene rainforests were probably the same way, teeming with life that left almost no trace. So we're forced to reconstruct an entire epoch from scattered clues. A jawbone here, a tooth there, occasionally a nearly complete skeleton if we're incredibly lucky. And from these fragments we try to understand a world that was nothing like our own. The early primates are the perfect example of this frustration. Somewhere during the Eocene, the ancestors of monkeys, apes, and eventually humans diverged from the ancestors of lemurs and lorises. This is one of the most important splits in primate evolution, the beginning of the lineage that would eventually produce us. And the fossil record for this transition is terrible, almost non-existent. We have early Eocene primates that look generally lemur-like, small, tree-dwelling, big-eyed creatures adapted for life in tropical forests. We have Middle Eocene primates that show some features suggesting they might be closer to monkeys and apes, and then we have late Eocene and early Oligocene primates that are clearly on the monkey and ape line. But the transitions, the species that actually show the evolutionary steps from one group to the other, missing, just gone, lost in millions of years of tropical rainforest that produced almost no fossils. There's a gap in our understanding here that's millions of years wide. We can't see the evolutionary innovations that made anthropoid primates, our direct ancestors, different from other primates. We can't trace the development of features like forward-facing eyes, grasping hands, enlarged brains, all the characteristics that would eventually make humans possible. The evidence is just not there, and this pattern repeats across dozens of mammal groups. The evolution of horses from small dog-sized forest browsers to large grassland grazers, critical transitional fossils missing. The development of whales from land-dwelling ancestors to fully aquatic mammals. Huge gaps in the Middle Eocene when the most dramatic adaptations must have occurred. The origin of bats, the only flying mammals, almost completely mysterious. We have early Eocene fossils of bats that already fully developed for flight, suggesting they evolved millions of years earlier, but we don't have the fossils of their flightless ancestors. They're just not there. Then there's the Eocene-Oligocene transition. 34 million years ago, something dramatic happened. The hothouse world ended. Not gradually, but relatively suddenly in geological terms. Within less than 1 million years, global temperatures dropped by 15 degrees Fahrenheit. Ice sheets formed in Antarctica for the first time in over 20 million years. The tropical forests that had covered huge portions of the planet retreated toward the equator, and a massive extinction event swept across the world. We know this happened. The geological and fossil evidence is clear, but we don't fully understand why. The leading theory involves changes in ocean currents. As continents continue drifting, the Drake Passage between South America and Antarctica finally opened wide enough to allow the Antarctic circumpolar current to form. This current isolated Antarctica, preventing warm tropical waters from reaching it and allowing it to freeze. The formation of Antarctic ice sheets then created a feedback loop, reflecting more sunlight, cooling the planet further, causing even more ice to form. But here's the problem. The timing doesn't quite work. Some evidence suggests the cooling began before the Drake Passage fully opened. Other evidence shows periods of warming in the middle of the overall cooling trend. The transition wasn't smooth. It was chaotic, stuttering, full of false starts and reversals, and the fossil record from this critical period is terrible. Fragmented, incomplete, full of gaps where we need continuous records but have almost nothing. What we do know is that this transition fundamentally changed which animals survived and which went extinct. The creodonts, gone, the brontotheres, extinct. Dozens of other mammal families that had thrived for millions of years, wiped out. In their place came new groups, ancestors of many modern mammals, animals adapted for the cooler, more seasonal world that was emerging. But the extinctions weren't random, and we don't fully understand the pattern. Some groups disappeared entirely. Others survived but were reduced to tiny remnant populations. Still others thrived during the transition, expanding their ranges as the tropics contracted. Trying to figure out what determined survival versus extinction is nearly impossible, because the fossil record has so many gaps. We're missing the environmental data, the climate records, the detailed species-by-species information that would let us reconstruct exactly what happened and why. And here's what makes this really frustrating for scientists. The Eocene-Oligocene transition is arguably the best recent analogue for what's happening to Earth's climate right now. We're living in a period of rapid warming, driven by rising CO2 levels. The Eocene was the last time Earth had CO2 concentrations similar to what we're heading toward. Understanding what happened then, how ecosystems responded, which species survived and which didn't, could give us crucial insights into what might happen in the next few centuries. But we can't fully understand it because the evidence isn't there. Continental drift destroyed it. Tropical preservation conditions prevented it from forming. Geological upheaval buried it or tilted it or fractured it until it became unreadable. We're left with a crucial period in Earth's history that we can only partially reconstruct. A climate transition we desperately need to understand but can't fully explain. The Eocene stands as a massive gap in our understanding of how Earth's climate and ecosystems function under extreme conditions. 22 million years of hothouse conditions that produced life forms we can barely imagine, and then wiped them away in a geological instant. A period when palm trees grew at the poles and crocodiles swam in Arctic rivers, when bizarre mammal lineages rose and fell without leaving clear explanations for their existence, and perhaps most importantly, a period that contained the evolutionary origins of our own lineage. Somewhere in those Eocene rainforests, among those fragmentary fossils and massive gaps in the record, our ancestors were evolving the characteristics that would eventually make humans possible. Enhanced vision, grasping hands, larger brains, social complexity. The foundations of human evolution were being laid, and we can barely see it happening. Because the Earth itself has erased the evidence, leaving us with questions we may never fully answer. Now, we need to talk about one of the most frustrating periods in Earth's entire history. Not because nothing happened, but because almost everything that happened left virtually no trace. Welcome to the Oligocene and Miocene epochs. 34 million to 5 million years ago, nearly 30 million years of Earth history that should be absolutely packed with answers to our biggest evolutionary questions. Instead, it's like someone took the most important chapters of Earth's autobiography and fed them through a shredder. Here's what we know was happening during this time. The planet was cooling, steadily, dramatically, transforming from the hot, humid world of the Eocene into something that would eventually become recognizable as the modern Earth. Antarctica, which had been forested and relatively warm just a few million years earlier, froze solid around 34 million years ago. Within a few 100,000 years, it went from a temperate continent with trees and rivers to a frozen wasteland covered in ice sheets miles thick. That transformation should have been documented in thousands of fossil sites across the globe. We should have layer upon layer of sediment showing the gradual shift from one climate to another, from one ecosystem to another. Instead, we have gaps, massive, inexplicable gaps where entire ecosystems simply vanish from the fossil record with no clear transition, no connecting evidence, nothing. But the cooling didn't stop with Antarctica. Over the next 30 million years, global temperatures continued their downward slide. The hot, jungle-covered world that had dominated Earth for hundreds of millions of years was dying, and something new was emerging. Grasslands. Now, grasslands might not sound particularly exciting, but this was one of the most revolutionary ecological transitions in Earth's history. For most of the age of mammals, the planet had been dominated by forests, dense, tangled, vertical ecosystems where success meant being able to climb, swing, hide in the canopy. Then, relatively suddenly in geological terms, huge swathes of those forests disappeared. They were replaced by open spaces, endless plains of grass stretching from horizon to horizon. This should be one of the best documented transitions in Earth's history. The shift from forest to grassland would have affected every animal on the planet. New species would have emerged to exploit the open spaces. Old species would have gone extinct or adapted. The fossil record should show us this transformation in exquisite detail, layer by layer, species by species. Except it doesn't. What we have instead are snapshots, brief windows into this 30 million year period, separated by enormous gaps. We have forest ecosystems from the early Oligocene, then millions of years of nothing. Then suddenly in the late Miocene we have vast grasslands with completely different animal communities. The transition between them, the actual process of transformation, is largely missing. And nowhere is this more frustrating than when it comes to our own ancestors. Because somewhere during the Oligocene and Miocene, something incredibly important happened. Apes evolved. Not just any apes, but the lineage that would eventually lead to humans. This should be the most intensely studied period in all of paleontology. This is when our family tree started branching. This is when the characteristics that make us human first began to emerge. Instead, what we have is what scientists politely call a substantial gap in the fossil record. What they mean is, we have almost nothing. Here's what we think happened, based on the fragmentary evidence we do have. Around 25 million years ago, during the Oligocene, primitive apes started appearing in Africa. These weren't like modern apes. They were smaller, more monkey-like, still spending most of their time in trees. But they had certain characteristics, dental patterns, limb proportions, skull shapes, that mark them as apes rather than monkeys. They were our ancestors, the beginning of our line. Then the fossil record goes dark. For millions of years we have almost nothing. A tooth here, a jaw fragment there, but no complete skeletons, no clear evolutionary sequences, no way to track how these primitive apes were changing and adapting. It's like trying to watch a movie when 90% of the frames are missing. You can kind of figure out what's happening, but you're guessing at most of it. When the fossil record picks up again in the middle Miocene, around 15 million years ago, everything has changed. Now we have multiple ape species spread across Africa, Europe and Asia. Some are small and gracile, others are massive, weighing hundreds of pounds. Some are clearly adapted for life in trees, others show early signs of terrestrial adaptation. The diversity is stunning, and the evolutionary relationships between them are almost impossible to untangle, because we're missing the connecting fossils that would tell us how they're related. These are called ghost lineages, evolutionary lines that must have existed, that had to have existed based on genetic and anatomical evidence, but which left almost no fossil trace. The mathematics of evolution tells us they were there. DNA analysis of modern apes confirms they existed. But the rocks are silent. Think about what this means. For roughly 10 million years, during a critical period when apes were diversifying and spreading across 3 continents, we have maybe a few dozen partial specimens, total. To put that in perspective, we have better fossil documentation of dinosaurs from 100 million years ago than we do of our own ancestors from just 20 million years ago. Why? What happened to all those fossils? Part of the answer is geology. The Oligocene and Miocene were periods of intense geological activity. Mountain ranges were forming. India was slamming into Asia, pushing up the Himalayas. Africa was drifting north, creating the Alps and closing the Tethys Sea. All this geological chaos was fantastic for creating dramatic landscapes, but terrible for preserving fossils. Fossilization requires very specific conditions. You need the right kind of sediment, the right water chemistry, the right rate of burial, and you need all of that to remain undisturbed for millions of years. But during the Oligocene and Miocene, vast areas of Africa and Eurasia were being uplifted, eroded, folded, and fractured. Sediments that might have contained fossils were being destroyed as fast as they formed. The climate chaos made things worse. Remember, this was a period of dramatic global cooling. But that cooling wasn't smooth and steady. It was punctuated by sudden climate shifts, periods of rapid change that could transform entire ecosystems in just a few thousand years. These rapid transitions were devastating for fossil formation. Here's why. Fossils form best in stable environments. Lake bottoms where sediment accumulates year after year, undisturbed. River deltas where flooding regularly buries organisms in mud. Stable forests where fallen trees and dead animals are slowly covered and preserved. But when the climate is changing rapidly, these stable environments disappear. Lakes dry up, rivers change course, forests die and are replaced by grasslands, which don't preserve fossils nearly as well. During the Oligocene and Miocene, Earth was experiencing some of the most dramatic climate swings in mammalian history. Temperatures would drop suddenly, then stabilize, then drop again. Rainfall patterns would shift, turning wet regions dry and vice versa. These fluctuations created an ever-changing mosaic of environments, none of them stable enough to preserve good fossil records. And it wasn't just our ancestors that vanished from the record. Entire families of animals evolved during this period with almost no connecting fossils. Modern horses, for instance. We know they evolved from small, multi-toed forest dwellers into large, single-toed plains runners during the Miocene. This transformation required massive changes to their anatomy, digestive system, behavior, everything. It should be one of the best documented evolutionary transitions we have, and in North America it is. The fossil record of horse evolution in North America is actually quite good. We can track the changes step by step. But in Eurasia and Africa, where horses also evolved and spread during the same period, the record is fragmentary at best. Whole branches of the horse family tree appear and disappear with no clear ancestry, no obvious descendants. They're evolutionary orphans, species that existed but which we can't connect to anything that came before or after. The same pattern repeats across dozens of mammal groups. Modern elephants evolved during the Miocene from smaller ancestors, but the transitional forms, the species that link primitive proboscideans to modern elephants, are mostly missing. We have the endpoints, but not the journey between them. Modern big cats evolved during this period. Lions, tigers, leopards all emerged from a common ancestor that lived sometime in the Oligocene or early Miocene, but we have almost no fossils showing how this diversification happened. The earliest clear lion fossil is only about 3.5 million years old, but genetic analysis tells us lions split from other big cats at least 10 million years ago. Where are those 6 million years of lion evolution? Gone, erased, lost to time. Even modern primates, our closest relatives, show the same frustrating pattern. Gorillas, chimpanzees, orangutans, all these species have ancient origins stretching back into the Miocene, but their fossil records are essentially non-existent. We have more fossil evidence of extinct ape species that aren't closely related to anything alive today than we do of the direct ancestors of our closest living relatives. This creates a bizarre situation. We know more about evolutionary dead ends than we do about successful lineages. The species that went extinct often left better fossils than the ones that survived. It's like having a history book where all the chapters about important civilizations have been torn out, but the footnotes about minor kingdoms that collapsed are still intact. And the grassland transition makes everything worse. Because grasslands are terrible for preserving fossils compared to forests and wetlands. In a forest, when an animal dies, it often falls into water or gets buried in soft, organic, rich soil. Perfect conditions for fossilization. But on a grassland, dead animals are exposed to scavengers, weather, and bacterial decay. Within weeks, most carcasses are scattered and destroyed. Only under very specific circumstances, like being buried by a flash flood or falling into a sinkhole, do they have any chance of fossilization. So as forests gave way to grasslands during the Miocene, the probability of fossil preservation dropped dramatically. And this happened exactly when apes were undergoing their most important evolutionary developments. The timing couldn't have been worse for paleontologists. But here's what really haunts researchers who study this period. It's not just that we're missing fossils, it's that we're probably missing entire species, entire evolutionary experiments that rose and fell, leaving no trace whatsoever. Genetic analysis of modern apes suggests there should have been dozens of ape species living during the Miocene, different lineages branching and evolving, competing for resources, adapting to new environments. The genetic diversity we see today could only have come from a much larger ancestral population with far more species than we've found fossils of. So where are they? How many species evolved and went extinct during those 30 million years without leaving a single fossil? How many potential ancestors to humans lived and died without us ever knowing they existed? The ghost lineages haunt us precisely because we know they must have been real, but we can't see them, can't study them, can't even properly acknowledge their existence except as gaps in our understanding. And those gaps have real consequences for understanding human evolution, because somewhere in those missing millions of years, something happened that set our lineage on a unique path. Somewhere between 25 and 5 million years ago, the ancestors of humans diverged from the ancestors of other apes. They developed characteristics that would eventually lead to bipedalism, tool use, enlarged brains, all the features that make us human. But we don't know when. We don't know how. We don't know what environmental pressures drove these changes, or what intermediate forms connected primitive apes to the first recognizable hominins. The Oligocene and Miocene should answer these questions. Instead, they mock us with absence. What we're left with is speculation built on fragments. We can guess that climate change played a role, that the spread of grasslands created new selective pressures, that competition between ape species drove innovation and adaptation. But we're guessing, building elaborate theories on foundations of sand, hoping that someday, somewhere, someone will find the fossils that fill in the gaps. Until then, these epochs remain the lost middle chapters, the crucial period between the ancient world of forests and the modern world of grasslands, the time when our ancestors transformed from generic apes into something unique, the 30 million years that should explain everything, but instead explain almost nothing. And the worst part? We'll probably never recover most of what's missing. Those fossils are gone, destroyed by the same geological and climatic forces that made this period so evolutionarily important. The evidence of how we became human is lost forever, eroded away into dust and scattered across ancient landscapes that no longer exist. But the story continues, because the few fossils we do have from the end of the Miocene show us something remarkable. By 5 million years ago, when the Miocene finally gave way to the Pliocene, apes had undergone a revolution. and somewhere among them, walking on two legs through the African grasslands, were the first creatures that looked almost but not quite like us. Now we need to talk about the period that should be the most important in human history, but instead represents one of the most frustrating gaps in the entire fossil record. The Pliocene epoch, 5 to 2.6 million years ago, the time when our ancestors stopped being apes and started becoming human. We know it happened, we can see the before and after. But the actual transition, the moment when everything changed, it's mostly missing. And here's what makes this particularly maddening. We're not talking about some obscure group of ancient reptiles that lived in remote corners of the earth millions of years before anything resembling humans existed. We're talking about our direct ancestors, the individuals who developed upright walking, tool use, enlarged brains, all the features that make us human. They lived relatively recently in geological terms. They left evidence of their existence. But we have so few fossils that you could fit nearly all the significant Pliocene hominin specimens in a single room. Think about that. The entire physical record of humanity's emergence as a distinct lineage could be stored in your living room. Every crucial fossil that documents our transformation from tree-dwelling apes to ground-walking tool users, a handful of partial skeletons, scattered bones, fragments of skulls. That's it. That's all we have to explain the most important evolutionary transition in our lineage, and it's not because nobody's looking. Paleoanthropologists have been searching East Africa for over a century. They've examined thousands of fossil sites, sifted through millions of tons of sediment, dedicated entire careers to finding the missing pieces of our origins. They found some remarkable things, sure, but the gaps between those discoveries are enormous. We have Lucy, the famous Australopithecus afarensis skeleton discovered in Ethiopia in 1974. She's about 3.2 million years old, and she's one of the most complete early hominin fossils ever found. About 40% of her skeleton survived, which in paleoanthropology terms makes her practically intact. She tells us that by 3.2 million years ago, our ancestors were definitely walking upright, had brains still similar in size to apes, but bodies that were starting to look human. She's a snapshot, a single moment frozen in time. But here's the problem. Lucy represents one individual who lived for maybe 20 or 30 years, 2 million years ago. We have very little from the 200,000 years before her, and not much more from the 200,000 years after. She's standing alone in a vast temporal emptiness, a single data point trying to represent hundreds of thousands of years of evolution. The other Australopithecine fossils we've found don't fill in the picture much better. They're scattered across time like breadcrumbs, each one separated from the next by gaps of 100,000, 200,000, sometimes 500,000 years. Imagine trying to understand a person's entire life story, but you only have photographs from when they were 2 years old, then 12, then 47, then 83. You could see they changed. You could guess at what happened in between. But you'd be missing almost everything that made them who they are. That's what we're dealing with in the Pliocene. We can see that something incredible happened. Apes became humans. But we're missing the actual process. And the gaps aren't random. They're systematic, concentrated in exactly the times and places where we most need evidence. Between 4 and 5 million years ago, right when the earliest hominins should have been diverging from other apes, we have almost nothing. A few teeth from Kenya, some skull fragments from Chad. These tantalizing hints that something was happening, but not enough to say what. Then there's the gap between 2 and 3 million years ago, right when the genus Homo, our genus, was emerging from Australopithecine ancestors. We have a handful of fossils that might be transitional forms, but they're so fragmentary and scattered that experts can't even agree on how many species they represent. Some researchers think there were 3 or 4 distinct human species coexisting during this period. Others argue for 6 or 7. A few think there might have been a dozen or more lineages, most of which went extinct without leaving any fossil record at all. They're arguing about ghost species, entire branches of the human family tree that we know must have existed based on genetic and geological evidence, but which have left no physical trace. And here's what makes the Pliocene gap so particularly frustrating. We know exactly where to look. The fossil evidence we do have points clearly to East Africa as the cradle of humanity. The Rift Valley region, stretching from Ethiopia through Kenya and Tanzania, that's where the hominin revolution happened. We know the location. We've identified the right geological formations. We found enough fossils to prove our ancestors were there. But the preservation is terrible. The conditions that made East Africa perfect for human evolution made it terrible for fossilization. Because here's the thing about fossils, they don't just happen. Fossilization requires very specific conditions. You need the right type of sediment, usually fine-grained material that can quickly bury and protect organic remains. You need the right water chemistry, minerals that can infiltrate and replace bone before it decays. You need geological stability. The fossil site has to remain undisturbed for millions of years, not get eroded away or destroyed by volcanic activity or tectonic movement. And you need luck. Even under perfect conditions, fossilization is incredibly rare. Most organisms that die are consumed by scavengers, decomposed by bacteria, scattered by weather, and disappear without a trace. Now take all those requirements and try to apply them to Pliocene East Africa. It doesn't work. The Rift Valley was, and still is, one of the most geologically active places on Earth. Volcanoes erupting regularly, earthquakes constantly shifting the landscape, rivers changing course every few thousand years. The environment was perfect for evolution, changing rapidly enough to create strong selection pressures, driving our ancestors to adapt or die. But that same dynamism was terrible for preservation. Volcanic eruptions would bury potential fossil sites under meters of ash. Tectonic activity would uplift sedimentary layers, exposing them to erosion. Rivers would cut through ancient deposits, washing away millions of years of history. Most of the time our ancestors were living in woodlands and grasslands, not near lakes or river deltas where fossilization is most likely. They were mobile, following resources across the landscape, not staying in one place long enough to create concentrated bone deposits. When they died, their bodies were probably quickly consumed by the rich scavenger community that existed in Pliocene Africa. Hyenas, vultures, insects. Within days or weeks, nothing would remain but scattered bone fragments, and those fragments would be exposed to weathering, cracking, disintegrating, turning to dust long before they had any chance of being buried and preserved. The few fossils we've found are the exceptions, the 1 in a million instances where everything went right. An individual happened to die near a lake or stream. Sediments happened to bury them quickly. Mineral-rich water happened to infiltrate the bones. The deposit happened to remain undisturbed for millions of years, and modern erosion happened to expose the fossil at just the right time for a paleoanthropologist to find it, before weather destroyed it. Every hominin fossil from the Pliocene represents a winning lottery ticket. Millions of our ancestors lived and died during this period, but we've found maybe a few hundred individuals, and most of those are represented by just a single bone or tooth. This creates enormous problems for understanding human evolution. We're trying to reconstruct the story of how we became human, but we're working with a tiny, biased, fragmentary sample of the actual population. It's like trying to understand American history, but the only evidence you have is 3 photographs from the Civil War, a diary entry from 1923, and a newspaper from 1967. You could see that things changed. You could guess at the major events. But you'd be missing almost everything. And the gaps create space for massive uncertainty and debate. Between the fossils we have found, there's room for almost any evolutionary scenario. Did early hominins evolve gradually, slowly accumulating human features over millions of years? Or did they evolve in rapid bursts, long periods of stasis interrupted by quick transformations? We can't tell because we don't have enough data points. How many species of early humans coexisted during any given period? We don't know. The fossils we have might represent distinct species, or they might just show normal variation within a single species. Did our ancestors develop upright walking first and then increase brain size, or did both happen together? The fossil record can support either interpretation. What about technology? We know stone tools appear in the archaeological record around 3.3 million years ago. But who made them? We have several hominin species from around that time, and we don't know which one invented tool making. Were they all using tools and only one group's tools got preserved? Or was tool use limited to a single innovative lineage? The gaps are big enough that we're still arguing about basic questions. And it's not just the quantity of fossils that's the problem, it's also their quality. Most Pliocene hominin fossils are fragmentary. A piece of skull here, a fragment of jaw there, a few scattered teeth. Paleoanthropologists have become incredibly skilled at extracting information from these fragments. They can estimate brain size from a piece of skull. They can determine diet from tooth wear. They can reconstruct posture from a single vertebra. But there are limits to what you can conclude from incomplete evidence. Every new discovery has the potential to completely overturn previous interpretations. It happened with Lucy. Before she was found, scientists thought early hominins had large brains and walked upright late in their evolution. Lucy proved them wrong. She had a small ape-sized brain but was clearly walking upright. It happened with Ardipithecus ramidus, discovered in Ethiopia and dated to 4 million years ago. Ardi, as she's called, showed that early hominins were even more ape-like than anyone had suspected, but also that they were experimenting with upright walking much earlier than we thought. Each major discovery rewrites part of the story, and between discoveries, we're left with massive uncertainties. There's another dimension to the Pliocene mystery that makes it even more frustrating. We know from genetic evidence that important things were happening during the periods where we have no fossils. Modern genetic analysis can look backward in time, using mutation rates and DNA differences between species to estimate when different lineages diverged. And that genetic clock tells us there were multiple branching events in the human family tree during the Pliocene. Times when populations split apart, evolved in isolation, developed into distinct species. But we can't match most of these genetic branching events to actual fossils. We know they happened, we can estimate roughly when they happened, but we don't know what those ancestral populations looked like, where exactly they lived, or how they were adapted to their environments. It's like knowing a movie has 12 major characters, but you've only seen 3 of them. You know the others exist. You can see their influence on the plot, but you have no idea what they look like or what they're doing when they're off screen. Some researchers think we're missing entire human species lineages that evolved, persisted for hundreds of thousands of years, and then went extinct without leaving any fossil trace we've discovered yet. They must have lived in regions we haven't adequately explored. Central Africa, for instance, where forest environments make fossil preservation even less likely than in the Rift Valley. Or they might have lived in areas that have since been destroyed by geological processes, their entire fossil record erased by volcanic activity or erosion. Or they might just be waiting to be found, buried in sediments we haven't excavated yet, in fossil sites we haven't discovered. Every year, new hominin fossils are found. Every few years, a major discovery rewrites part of the story. In 2015, researchers announced Homo naledi, a strange human species from South Africa that might be as young as 300,000 years old, but has a bizarre mix of primitive and modern features. In 2019, a new species, Australopithecus deiremeda, was described based on fossils from Ethiopia, proving that multiple hominin species really were coexisting in the same region. Each discovery fills in a tiny piece of the picture, but the picture is so enormous and we have so few pieces. The Pliocene remains mostly mysterious, a crucial chapter in human history, written in a language we can barely read, with most of the pages missing, and that gap, that massive hole in our understanding of our own origins, it haunts paleoanthropology. Because unlike the extinction of the dinosaurs or the evolution of early mammals, this isn't ancient history. This is us, our direct ancestors, the individuals who gave us our bipedal posture, our capacity for tool use, the foundations of our enlarged brains. We should know their story. We desperately want to know their story. But the Earth has kept most of it hidden, buried under millions of years of geological change, erased by the same dynamic processes that drove our evolution in the first place. We're left grasping at fragments, building theories on scattered bones, arguing over interpretations of incomplete evidence. The Pliocene mystery remains one of the most significant gaps in the entire history of life on Earth, and it's not getting easier to solve. But the story gets even stranger when we move forward in time, because the gaps don't end with the Pliocene. Now here's where things get really strange, really uncomfortable for anyone who likes their history neat and tidy. We've talked about gaps in the fossil record from millions of years ago. The Paleocene, the Miocene, entire geological epochs where we're missing massive chunks of information. That makes sense, right? Time destroys evidence. Rocks get subducted, eroded, buried under miles of sediment. The older something is, the less likely we are to find it. Except that logic completely breaks down when we get to recent history. The Pleistocene epoch. 6 million years ago to 11,700 years ago. The Ice Ages, the time when humans evolved from primitive hominids into behaviorally modern people. The period when we spread across the entire planet, developed language, created art, invented tools sophisticated enough to hunt woolly mammoths and saber-toothed cats. This is recent. This is practically yesterday in geological terms. This is so recent that some Pleistocene animals are still alive. Elephants, rhinoceroses, lions. These are Pleistocene species that survived into the modern world. And yet, we have absolutely massive gaps in our understanding of this period. Gaps that make no sense. Gaps that seem to violate everything we think we know about how archaeology and paleontology work. Here's the paradox that keeps paleontologists awake at night. We have better, more complete fossils of dinosaurs that lived 66 million years ago than we do of human ancestors who lived 100,000 years ago. Think about that. Really think about it. a Tyrannosaurus rex that died 66 million years ago, we can find nearly complete skeletons. We can study their bone structure, analyze their growth patterns, determine what they ate and how they moved. Museums around the world display T-Rex skeletons that are 70, 80, sometimes 90% complete. But a Neanderthal who died 40,000 years ago? We're lucky if we find a jawbone and a few teeth. Most Neanderthal specimens are so fragmentary that we're reconstructing entire populations from partial skulls and scattered limb bones. The Denisovans, an entire human species that lived across Asia until maybe 30,000 years ago. We've found exactly one finger bone, a handful of teeth, and a piece of skull. That's it. That's everything we have from an entire species that was spread across millions of square miles and survived for hundreds of thousands of years. We've identified these people, mapped their genome, figured out they interbred with modern humans and Neanderthals, determined they adapted to high altitudes and developed maritime technologies, all from a finger bone found in a Siberian cave in 2008. It's absurd. It's like trying to reconstruct the entire history of the Roman Empire from a single coin and 3 bricks. And it gets worse, because the Denisovans aren't alone. In 2004, scientists discovered Homo floresiensis, the so-called hobbits, on an Indonesian island, a completely unknown human species that survived until maybe 50,000 years ago. We had no idea they existed. None. Then suddenly we're digging up skeletons of 3-foot-tall humans with brains the size of chimpanzees, who somehow figured out how to make sophisticated stone tools and hunt dwarf elephants. In 2015, we found Homo naledi in South Africa, another completely unknown human species. Thousands of bones in a single cave system, and we still can't figure out how old they are. Initial estimates put them at 2 million years old based on their anatomy, but dating of the fossils suggested they might have survived until 230,000 years ago. That would mean they were alive at the same time as early modern humans. How do you lose an entire human species? How do you lose multiple human species? These aren't microscopic organisms. These are large mammals with complex social structures who made tools, used fire, buried their dead. They left footprints. They created archaeological sites. They should be everywhere in the fossil record. But they're not. They're ghosts, shadows. We know they existed only because of a handful of chance discoveries in caves and volcanic ash deposits where conditions happened to be perfect for preservation. The conventional explanation is that the Pleistocene ice ages destroyed most of the evidence, and that's partially true. For 2.6 million years, massive ice sheets advanced and retreated across the northern hemisphere. At the peak of glaciation, ice up to 2 miles thick covered Canada, most of northern Europe, and vast stretches of northern Asia. That ice was like a continental bulldozer. It scraped away topsoil, crushed rock into gravel, obliterated everything in its path. When the glaciers finally retreated about 11,700 years ago, they left behind landscapes completely transformed. Valleys had been carved into fjords, mountains had been ground down, river courses had been completely rerouted. Any archaeological sites, any human habitation areas, any evidence of populations living in those regions was simply erased. Ground into dust and scattered by meltwater floods that were bigger than anything in recorded history. So, that explains the gaps in the glaciated zones. But humans didn't just live under the ice. They lived in Africa, Asia, Australia, South America, regions that were never glaciated. Where's all their evidence? This is where the paradox gets even stranger. Because we're missing more than just fossils. We're missing archaeological sites. We're missing the places where people actually lived. Archaeological sites older than 50,000 years are extraordinarily rare. Not just uncommon, rare to the point of being almost non-existent. We can count on our fingers the number of well-preserved archaeological sites from before 50,000 years ago. And most of those are caves, places where unusual conditions allowed preservation. Open-air sites, campsites, hunting grounds, processing areas, the places where people actually spent most of their time. Almost nothing survives. But here's what really doesn't make sense. During the Pleistocene, there were millions of humans living across multiple continents for hundreds of thousands of years. They were making tools constantly. Stone tools, bone tools, wooden implements. They were processing food, creating hearths, building shelters. They should have left behind billions of artifacts. Even if 99% of those artifacts were destroyed by natural processes, we should still be finding them everywhere. Every eroding riverbank should be full of stone tools. Every cave should contain multiple occupation layers. The archaeological record should be dense and continuous. But it's not. It's sparse, fragmentary, full of massive temporal gaps where we have essentially nothing. And then there's the megafauna extinction. Between about 50,000 and 10,000 years ago, the majority of large mammal species on Earth went extinct. Woolly mammoths, mastodons, saber-toothed cats, giant ground sloths, cave bears, woolly rhinoceroses. In North America alone, we lost 34 genera of large mammals. In South America, 50 genera disappeared. Australia lost nearly all its megafauna. This is one of the most dramatic extinction events in Earth's history, and it happened right when humans were spreading across the globe. The correlation is obvious. We showed up, the megafauna disappeared. But here's the problem. We have almost no direct evidence of humans hunting these animals to extinction. Yes, we have a handful of kill sites. Yes, we have mammoth bones with spear points embedded in them. But we're talking about dozens of sites documenting the extinction of hundreds of species across multiple continents. The math doesn't work. If humans hunted mammoths, mastodons, and giant sloths to extinction, there should be thousands of kill sites, massive bone beds full of butchered remains, processing areas where people systematically harvested these animals generation after generation. Where are they? Where's all the evidence of this supposed extinction-level hunting pressure? Most archaeological theories assume it's missing because of preservation bias. Kill sites in open areas were destroyed by erosion and glaciation. The evidence was there, but time destroyed it. Maybe. But that explanation is starting to wear thin when you realize just how much evidence is missing. And then there's the sea level problem. During the ice ages, when glaciers locked up enormous amounts of water, global sea levels were 300 to 400 feet lower than today. That exposed vast areas of continental shelf that are now underwater. The Bering Land Bridge between Asia and North America, that was thousands of miles of open grassland. The Indonesian archipelago, that was a single continuous landmass called Sunderland, bigger than India. The Persian Gulf, that was a river valley with lush vegetation and abundant resources. These weren't marginal environments, these were prime real estate. Coastal areas with access to both marine and terrestrial resources. Exactly the kind of places where human populations would thrive. And we've lost all of it. When the glaciers melted and sea levels rose, hundreds of thousands of square miles of human habitation area went underwater. Not gradually, but catastrophically. There's evidence of rapid sea level rise events where ocean levels jumped 10, 15, even 20 feet in a matter of decades. Imagine living in a coastal settlement and watching the ocean advance inland by miles every generation. Everything your ancestors built, every sacred site, every settlement, every artifact, all gradually submerged under hundreds of feet of water. That's what happened to our Pleistocene ancestors, and it means the majority of human activity during the ice ages is now sitting on the ocean floor under sediments and marine growth, completely inaccessible to archaeologists. We've done some underwater archaeology in shallow areas, and every single time we find unexpected things. Submerged caves with Ice Age art, drowned river valleys with stone tools and animal bones, ancient shorelines with evidence of sophisticated maritime cultures that we had no idea existed. But we've barely scratched the surface. The continental shelves represent millions of square miles of unexplored archaeological territory. We have better maps of Mars than we do of the Ice Age landscape sitting under a few hundred feet of seawater off our coasts. So here's the uncomfortable question that's starting to emerge in archaeological circles. What if we're missing more than just hunter-gatherer campsites? What if there were more complex societies during the Pleistocene than we've been assuming? This is controversial, really controversial, because it challenges fundamental assumptions about human cultural evolution. The standard narrative says complex societies emerged only after the Ice Ages ended, only after agriculture was invented about 10,000 years ago. Before that, humans were simple hunter-gatherers living in small bands, no permanent settlements, no large-scale construction, no sophisticated social organization. But that narrative is based on the assumption that we have a reasonably complete archaeological record, and we're starting to realize we don't. We're missing enormous chunks of time and space. The gaps are so large that we literally cannot say with certainty what was or wasn't happening during the Pleistocene. Göbekli Tepe in Turkey has already forced us to revise our assumptions. Built 11,500 years ago by people who supposedly hadn't invented agriculture yet, it features massive stone pillars carved with sophisticated artwork, organized into complex circular structures that required coordinated labor by hundreds of people. This isn't supposed to exist. According to the old models, people this early shouldn't have been capable of this kind of construction. But there it is, undeniably real, forcing us to acknowledge that maybe our ancestors were more capable than we've been assuming, and if Göbekli Tepe exists from right at the end of the Ice Ages, what else might have existed during the Ice Ages that we simply haven't found yet? What got submerged under rising seas or obliterated by advancing glaciers? We don't know. We can't know. The evidence is gone. What we do know is this. The Pleistocene was a time of dramatic environmental change, repeated catastrophes, and human populations pushed to the absolute limits of survival. The same conditions that created the genetic bottleneck 900,000 years ago were repeated over and over during the Ice Ages. Glacial advances, mega-droughts, volcanic eruptions, rapid climate shifts. Each of these events would have destroyed populations, obliterated archaeological sites, and reset human cultural development in affected regions. The humans who survived were tough, adaptable, and innovative. But they were also living on borrowed time, knowing that at any moment the climate could shift and everything they'd built could be destroyed. Maybe they created sophisticated cultures that left no trace. Maybe they developed technologies that seemed advanced for their time but were built from materials that don't survive. Maybe they told stories and created art and organized themselves in complex ways that we'll never discover because all the evidence has been destroyed. Or maybe they really were simple hunter-gatherers and were just dealing with normal preservation bias magnified by Ice Age catastrophes. The paradox is that we're too close to this period to have the kind of geological preservation that helps us with older fossils, but too far away to have the kind of detailed archaeological record we get from more recent periods. We're stuck in a gap. A massive, frustrating gap in the most important period of human prehistory. And the more we learn, the more we realize just how much we don't know. So you're probably wondering, if all these incredible creatures existed, if entire ecosystems rose and fell over millions of years, why don't we have more evidence? Why are there these enormous gaps in the fossil record where entire epochs seem to just vanish? Why can't paleontologists just dig deeper and find all the missing pieces? Here's the uncomfortable truth. Fossilization is unbelievably, spectacularly, almost impossibly rare. Think about every animal that dies today, every bird that falls from the sky, every deer that collapses in the forest, every fish that stops swimming and sinks to the ocean floor. How many of them will become fossils? How many will still exist as recognizable remains 10 million years from now, let alone 50 million or 200 million? The answer is almost none, effectively zero. Because here's the thing about fossilization. It requires a perfect storm of conditions that almost never happens. First, the organism has to die in exactly the right place. Not on a hillside where scavengers will tear it apart and scatter the bones. Not in a stream where the current will break the skeleton into pieces. Not in the open where sun and weather will bleach and crumble everything into dust. It needs to die somewhere it can be buried quickly, before decomposition and scavengers do their work. A riverbed where sediment will cover it during the next flood. A mudslide that entombs it instantly. A peat bog where the chemistry of the water prevents decay. Already we're down to maybe 1 in a million organisms that even gets to this stage. But that's just the beginning. Once buried, the organism needs to stay buried, for millions of years, undisturbed. While chemical processes slowly replace organic material with minerals, turning bone into stone. This process, called permineralization, requires specific groundwater chemistry, specific mineral content, specific pH levels. Get any of it wrong and the bone just dissolves away, leaving nothing behind. Even when everything goes right, the fossilization process is selective. Hard parts, bones and shells and teeth, those might survive. But soft tissue, skin, muscles, organs, feathers, gone. Completely erased from the geological record except in the rarest of circumstances. This means we're essentially working with skeletal blueprints, trying to reconstruct entire living organisms from their bones alone. Imagine trying to understand modern elephants if all you had were their skeletons. Would you know about their trunks, their intelligence, their complex social structures, their ability to communicate through subsonic frequencies? Not from bones alone. You wouldn't. And we've only just started listing the problems. Let's say an organism beats all those odds. It dies in the right place, gets buried quickly, stays buried, and successfully fossilizes. Now it needs to survive millions of years of geological violence, because the Earth doesn't just sit still. The Earth is constantly destroying its own history. Plate tectonics is the great eraser of the fossil record. Every year, tectonic plates drift a few centimeters. Doesn't sound like much, but over millions of years, those plates move thousands of miles. They collide, creating mountain ranges that thrust ancient seafloors into the sky. They split apart, opening ocean basins where dry land used to be, and most destructively they subduct. One plate slides beneath another, dragging down into the mantle, where temperatures and pressures turn everything to magma. Gone. Melted back into molten rock. Entire continents worth of fossils, entire epochs of evolutionary history, just recycled back into the Earth's interior. The Pacific Ocean floor, for example, is almost entirely less than 200 million years old. Everything older has been subducted. Millions of years of ocean life, entire marine ecosystems from the Paleozoic and early Mesozoic eras, destroyed by geological recycling. We'll never know what lived there, never see fossils of those organisms. The evidence has literally melted away. But subduction isn't the only destroyer. Mountain building crumples rock layers like paper, fracturing fossils into unrecognizable fragments. Volcanic eruptions bury fossil beds under meters of igneous rock, or heat them until organic remains are burned away completely. Metamorphism, the transformation of rock under heat and pressure, obliterates fossils by recrystallizing the very stone they're preserved in. There are vast regions where Paleocene and Eocene rocks exist, but any fossils they once contained have been destroyed by metamorphic transformation. The rocks are still there, the history is gone. Then there's erosion, the slow-motion destruction of everything. Mountains rise and immediately wind and water begin tearing them down. Every rainstorm carries away a little more sediment. Every freeze-thaw cycle cracks rocks apart. Every river carves deeper into ancient layers. Over millions of years, erosion can remove thousands of feet of rock, and with it, every fossil that rock contained. Entire geological formations representing millions of years of time worn away to nothing and washed into the ocean. And here's what makes it even worse. The fossils we do find are the result of this impossible process working in reverse. Erosion has to remove just enough rock to expose the fossil layer, but not so much that it destroys the fossils themselves. Then, by pure chance, a paleontologist has to happen to be in that exact spot during the brief geological moment, maybe a few hundred years, when the fossils are exposed before erosion finishes destroying them. The odds are astronomical. Most fossils that survive fossilization and millions of years of geological violence never get discovered. They're buried under cities, highways, farmland. They're underwater. They're in remote mountains or deep jungles or vast deserts where no paleontologist will ever look. They're exposed during a storm and eroded away before anyone sees them. They're found by people who don't recognize them as fossils and just leave them there. Professional paleontologists estimate that we've discovered less than 1% of all fossils that ever existed. 1%. And remember, only a tiny fraction of organisms that ever lived became fossils in the first place. We're looking at multiple layers of improbability. 1 in 1,000,000 organisms fossilize. 1 in 100 fossilized organisms survive to the present. 1 in 100 surviving fossils ever get discovered. Do the math. For every fossil in a museum, there might be 1 billion organisms that lived and died without leaving any permanent trace. This preservation bias gets even more complicated when you consider environment. Some environments are fantastic for fossil preservation. River deltas, lake beds, coastal lagoons, places where sediment accumulates steadily and buries things quickly. These environments are overrepresented in the fossil record. We have detailed knowledge of ancient swamps and riverbanks because those are the conditions that preserve fossils best. But mountains, forests, grasslands, these environments rarely preserve anything. An animal dies on a hillside and the body's exposed to scavengers, weather and gravity. Bones scatter down slopes, break apart and disappear. 1,000,000 years later, erosion might remove that entire hillside, and there's nothing left to find. This means entire ecosystems are nearly invisible to paleontology. We know far more about ancient coastal wetlands than we do about ancient mountains, not because mountains were less important, but because mountains don't preserve fossils well. And soft-bodied organisms might as well not exist as far as the fossil record is concerned. Jellyfish, worms, slugs, anything without hard parts, they decay completely within days or weeks. The exceptional fossil sites that do preserve soft tissue, places like the Burgess Shale or the Solnhofen limestone, these are so rare and so celebrated precisely because they're bizarre anomalies. The normal fossil record tells us almost nothing about soft-bodied life. This creates enormous blind spots in our understanding. Think about modern ecosystems. In any environment, soft-bodied invertebrates often outnumber organisms with hard parts by orders of magnitude. Worms, insects, spiders, they're everywhere, forming the foundation of food webs. But in ancient ecosystems, they're almost completely absent from the fossil record. We're missing entire trophic levels, entire groups of organisms that must have existed but left no trace. And behavior? Forget about it. Fossils can tell us what an organism looked like, roughly how it moved, sometimes what it ate, but how it communicated, how it raised its young, how it interacted with others of its species. Gone. Occasionally we find trackways showing multiple animals moving together, suggesting herd behavior. Sometimes we find nesting sites or burrows, but these traces are incredibly rare for the vast or majority of extinct species. We have no idea how they actually lived. Migration patterns, seasonal behaviors, mating displays, hunting strategies, all the things that make organisms interesting, that define how ecosystems function, they're invisible to paleontology. We're working with shadows of shadows, fragments of evidence, trying to reconstruct the full richness of ancient life. The numbers are sobering when you really think about them. There are somewhere around 300,000 described fossil species. Sounds like a lot until you realize there are over 8 million species alive today, and life has been evolving for 3-5 billion years. Conservative estimates suggest that over 5 billion species have existed throughout Earth's history. We've found fossils of 300,000 of them. That's 0.6%. We're missing more than 99% of all species that ever lived. And for the species we have found, we typically have only a handful of specimens, sometimes just one. Entire genera, even entire families, known from a single partial skeleton found in one location. We're trying to understand global ecosystems and evolutionary patterns from a sample size that would be laughably inadequate in any other scientific field. It's like trying to understand human civilization by examining 3 random artifacts from different centuries found in different countries. You might learn something, but you'd miss most of the story. Then there's the problem of changing sea levels. Over geological time, sea levels have fluctuated wildly. During ice ages, when water is locked up in glaciers, sea level drops hundreds of feet. Coastlines extend far out onto what is now the continental shelf. Entire landscapes emerge from the sea. Then the ice melts, and sea level rises, flooding those coastal plains completely. This has happened dozens of times over the last few million years alone. Every time sea level rises, it drowns coastal ecosystems. Forests become seabed, rivers disappear underwater, and any organisms living in those environments, any evidence of their existence gets buried under marine sediments. Later, when sea level drops again, these flooded landscapes are exposed to erosion, wearing away the evidence even further. If any early human populations lived on these coastal plains during the ice ages, and there's every reason to think they did, coastlines are incredibly resource-rich environments. Their settlements are now underwater, buried under hundreds of feet of sediment or eroded away entirely. We're blind to vast swathes of recent prehistory simply because the places people might have lived are now ocean floor. The Bering Land Bridge connecting Asia and North America, drowned. The Sunda Shelf connecting Southeast Asian islands, underwater. The Persian Gulf, once a river valley, now entirely submerged. Each of these regions might have supported substantial populations during Ice Age periods when they were dry land, and we'll probably never find evidence of it because that evidence is either underwater or destroyed. Archaeological sites on modern coastlines fare little better. Erosion is relentless. Every storm cuts away at coastal cliffs. Every hurricane reshapes beaches. Over just a few centuries, significant archaeological sites can be completely erased. Extend that over millennia, and anything within miles of the coast is at risk. Ancient harbour cities, trading posts, fishing villages, they're the first to go, worn away by the same ocean that once sustained them. The deeper you look into the mechanisms of preservation and destruction, the more miraculous it seems that we know anything at all about the distant past. Every fossil is a winner of a 1,000,000,000 lottery. Every complete skeleton is impossibly lucky. Every glimpse we get into ancient ecosystems represents conditions aligning perfectly across millions of years. And the hardest part? Accepting that some questions will never have answers. There are mysteries in the fossil record that aren't mysteries because we haven't looked hard enough or thought carefully enough. They're mysteries because the evidence is gone, destroyed, erased, melted back into the mantle or worn away by wind and water. No amount of digging will ever find fossils that no longer exist. Paleontologists know this. They've made peace with it. Their job isn't to reconstruct every detail of prehistory. That's impossible. Their job is to work with the fragments that survived, to squeeze every bit of information from the tiny fraction of evidence that made it to the present day, and to acknowledge honestly the enormous gaps in our knowledge. The great chapters of Earth history that are lost forever because stone crumbles and time is merciless. But somehow, from that impossibly sparse record, they've reconstructed the broad outlines of life's history on Earth, the rise and fall of dinosaurs, the age of mammals, the branching tree of human evolution. It's detective work with 99% of the evidence missing. And what they've discovered is extraordinary. Still, we must remember what we don't know. The gaps exist, they're real, and they're permanent. So here we are, at the end of this journey through prehistory's greatest mysteries. And if you're still awake or drifting in that pleasant space between consciousness and sleep, let's think about what we've actually discovered tonight. Because here's the thing, we've covered 66 million years of Earth history, walked through entire epochs where continents shifted, climates transformed, and life evolved in directions we're only beginning to understand. And you know what the most honest thing I can tell you is? We barely know anything. Those gaps we've explored tonight, the Paleocene forests we can only glimpse in fragments, the Eocene jungles that left behind more questions than answers, the Oligocene transition that rewrote the rules of life, the Miocene savannas where our ancestors learned to walk upright. They're not bugs in our understanding. They're features. They're reminders that Earth's story is almost incomprehensibly vast, and that human knowledge, impressive as it is, can only illuminate tiny patches of that darkness. Think about this for a moment. Every single day, somewhere on Earth, a paleontologist uncovers something that shouldn't exist according to our current models. A fossil in the wrong geological layer, a species that evolved millions of years earlier than we thought possible. Evidence of climate shifts we never predicted. Stone tools where there shouldn't be any humans. Each discovery is like turning on a light in one room of a mansion with 10,000 rooms. Yeah, now we can see what's in this particular space, but it also reveals dozens of new doorways leading to places we didn't even know existed. Last year, researchers found evidence of complex tool use in North America 30,000 years earlier than previously believed. That discovery didn't just add information, it fundamentally changed our understanding of when humans arrived in the Americas and what routes they might have taken. One discovery, entire textbooks rewritten. 2 years ago, scientists discovered a previously unknown human species in the Philippines, Homo luzonensis, living on islands at the same time as Neanderthals, Denisovans, and modern humans. We had no idea they existed. Their DNA hasn't survived, so we can't sequence it. We don't know how they got to those islands or what happened to them. They're ghosts, just like the gaps we've explored tonight. And that's what makes this so fascinating. These aren't puzzles with missing pieces that we'll eventually find under the couch. These are puzzles where most of the pieces were destroyed millions of years ago, and we're trying to reconstruct the image from the few fragments that accidentally survived. The fossil record preserves maybe one organism out of every 10,000 that lived. Soft tissue decays, bones scatter, geological processes grind evidence into dust. Most of what happened in Earth's history left no trace whatsoever. The fact that we know anything about the Paleocene or the Eocene or the Oligocene is actually miraculous. But you know what? That makes every discovery more precious. Every fossil, every ancient pollen grain, every preserved footprint becomes a message from an almost unimaginably distant past. Voices from creatures that have been extinct for longer than humans have existed, telling us stories we're only beginning to learn how to hear, and we're getting better at hearing them. New technologies are revealing secrets locked in rocks that previous generations couldn't access. CT scanning lets us look inside fossils without destroying them. Ancient DNA analysis can extract genetic information from samples we thought were hopeless. Isotope analysis tells us what extinct animals ate, what temperature they lived in, how they moved across landscapes. Every year the gaps get a little smaller. Not much, maybe a few thousand years here or there in timescales spanning millions. But those small victories matter. They're proof that the unknown isn't unknowable, just not known yet. If you've enjoyed this journey through the gaps in Earth's history, if these ancient mysteries have sparked something in your imagination, or helped you drift off to sleep thinking about deep time and lost worlds, do me a favour. Drop a comment telling me where you're watching from. Are you falling asleep in Toronto? Listening during a late shift in Tokyo? Maybe you're somewhere I've never heard of, some small place with its own ancient rocks and hidden histories. Hit that like button if you want more videos exploring the mysteries science can't quite explain yet. And subscribe, because we're just getting started. There are so many more gaps to explore, so many more mysteries hiding in the spaces between what we know, because ultimately that's what makes us human. Not that we know everything, but that we keep looking, keep digging, keep asking questions even when the answers are separated from us by millions of years and countless catastrophes. We're descendants of survivors, products of bottlenecks and climate disasters and evolutionary experiments that somehow worked out. We're storytelling apes trying to understand a planet that existed for billions of years before we showed up and will exist for billions more after we're gone. And honestly, there's something deeply comforting about that. Something peaceful in accepting that we're just one brief chapter in an impossibly long book, most of whose pages have been lost to time. So sleep well if that's where you're headed. Dream of ancient forests and lost oceans and creatures that will never be fully known. The gaps will still be here tomorrow, waiting to be explored.